So we have some sort of this is O here. Okay, that's fine. So we have some sort of this. We have two carbonyl groups, and then you could say this is a carboxyl group actually instead. So I'm thinking of a decarboxylation reaction. I'm thinking about maybe some sort of because they're all ketones. Maybe some sort of ketone tautomerization kind of reaction here. So that's where my head is thinking right now, where I'm what this problem is approaching. And this here I have the first step here is NaOET. And in ethanol here. So this is not a bulky base. This is a relatively easy base. So this here would actually be a E2 reaction. And where is it going to eliminate? Which hydrogen is going to eliminate? It's going to eliminate the most acidic proton, right? It moves the acidic proton. And where is the most acidic proton in this case? It would obviously be this hydrogen here. These two hydrogens here would be the most acidic ones because again, I have these guys here are, again, I have a dipole moment here. These two are negatively charged, which means that this here is a positively charged, which creates these guys here are very, very positively charged to help stabilize these guys here, which means I have this hydrogen will probably be deprotonated. So how I would do that is this breaks down to, again, I have Na plus, and then I have, or Na, let me do this in colors. This is Na plus, and this is the anion OET minus. What it's going to do, it's going to eliminate through this, it's going to eliminate here and create a, it's going to deprotonate this here. So sorry, it's not an E2. It's going to just deprotonate this proton here. So I'm going to get something like this. And this is, again, this is actually pretty stable because I have, again, the inductive properties of the two carbonyl groups here help stabilize this guy here. This guy's a secondary carbocation, right? So it's going to be actually stabilized by these two. It's going to be stabilized by the two oxygens here, which is good. So that's my first step. Second step is I'm going to, what am I doing? Let me go with this. I'm going to go right here. I'm going to add, this is a 3-chained carbon, so CH3, CH2, CH2, and Br. So I'm going to add some sort of alkyl group here, right? So this is actually very, very easy. Again, this negatively charged is going to bond to this. Oh, whoops. It's going to attack this bromine here. It's going to kick out this bromine, and then I'm going to get something like this. So I have to redraw my compound here. So here's double bond O, double bond O. This here was bond O, bond, bond. And this here becomes something like this. So there's a 3-carbon chain, right? Something like that. So this here would be my, and I get Br minus as my side product. So this is, there's a Br minus somewhere floating around. Or, yeah, Br minus here. Floating around as my side product. That's fine. So I get this compound here. What's going to happen now is I have dilute NaOH, sodium hydroxide, and heat. So what is that going to do? It's going to do a, it's going to become, let's see, I have dilute NaOH and heat would mean that I am now, this is a hydrolysis reaction, right? This is a hydrolysis reaction because currently I have an ester, and then it's going to hydrolysis. Again, the opposite of condensation here. Dilute NaOH and heat, right? If I had concentrated NaOH, I would actually produce, remember, it's an esterification reaction is equilibrium, right? If I were to have concentrated acid, it's going to push towards the, or base is going to push towards the ester. If it's a dilute NaOH, it's going to do the backward reaction and create the carboxylic acid and the alcohol. So in this case, I have, this is dilute NaOH and heat will then create a hydrolysis reaction here. So the hydrolysis, what it is going to, again, as you can see here, this is the alcohol part. So let me draw this in blue. This here is the, this here is the alcohol part, and this here the rest of this guy here would be the carboxyl part. So basically what it does is going to hydrolyze this. This is going to cleave this kind of bond here, and it's going to make a carboxylic acid and and alcohol with the acid workup here. So let me so this here you actually also requires an acid workup. So this is dilute NaOH. Sorry. I think that's number 4. So let me actually break this. I'll do the acid workup in a different step here. But this is going to create, again, my carboxylic acid, which is stated like this. So I'm still in box mode, sorry. Which we get 1, 2, 3. So I have double bond O here, bond OH. This here is my carboxylic acid plus, and then I'm going to get basically whatever the attachment here, right? I have a 2-carbon O group, right? And it's going to be stabilized by this Na, positive Na. So this here is 1, 2. This here is O. There's O minus here. And let me do that in blue for you, because I said blue was blue negative. Give me a second. Just don't want to confuse you folks. Oh, sorry, red as negative here. So this here is a negative oxygen, and it's actually stabilized by the sodium proton that we have here. So this here is stabilized. So we have the carboxylic acid and kind of our alcohol, but it's not alcohol without the hydroxyl group, obviously. So we need acid workup, which is number 4. 4 is H3O plus, right? H3O plus. And basically what it's going to do is this is going to attach to this guy and then kick out one of these guys here, which means I form my alcohol as well. So this here is my again, my carboxylic acid is not being affected right now. OH plus, and then I have an alcohol, an ethanol group here. Sweet. Okay, and then finally, my last step is heat, right? So what does heat do? So heat here, in this case, heat here with if I'm heating my carboxylic acid, what it's going to do is going to decarboxylate my entire my thing here. It's going to decarboxylate it here. So let me look at my target. What is my target here? What is my target? Oh yes, this is the heat part, right? So it says heat. What it does is going to break up my my carboxyl group here. As you can see, let me just draw this out for you. This here is actually a CO2 group, right? I have this carbon here in the middle. I have 2 oxygens and the hydrogen here. So what's going to do is actually this the negatively charged oxygen here is going to then attack this hydrogen here. This is going to then collapse on itself, and then it's going to break up the entire carboxylic acid. And this is done in the presence of heat, right? So this is done in the presence of heat. Oh, whoops, sorry. This is heat, and this is 100 to 150 degrees Celsius. I'm actually not sure about the temperature, but I'm assuming they're right here. And then what it's going to do is going to then break up this guy here, and I'm going to get something like this. This would be a OH group. Yeah, I have an OH group like so. I actually no, my intermediate here is I have a double bond OH, right? O and then H here, and this here is a positive. So this is my intermediate. Oh, my positive is in blue, sorry. So I'm just drawing out the intermediate for you. This is the positive charge here. And then I also have, this is still something like this. But then again, this entire thing is being decarboxylated, right? So this entire thing was CO2, right? So it actually gets removed here. This is CO2. So I'm only drawing these 3 carbons here. So I have 1 and then basically 2. So I have 1, 2, and 3 here. So this here would be my kind of compound like so. And this here this has a negative charge right here because again, this is through the decarboxylation of this is a decarboxylation reaction. This here has a negative charge, and again, this negative charge is going to then attack this oxygen here. This is going to kick out one of my hydrogens here, which means I get this is a tautomerization. This is a ketone enol tautomerization. So this here becomes, this here is ketoenol, ketoenol. And what it's going to get is I'm going to get a double bond. I'm going to create OH group here. I'm going to get a double bond like so, and then it's going to do something like this. And then what it can do is, again, it can tautomerize to form a different compound. Okay, tautomerize to form a ketone here, right? So I have O here, and then my compound here. So these two groups are this. So let me actually, no, this here, this step is the tautomerization. This is the ketoenol, right? This here was an enolate before, enolate, and this here is a ketone. So this is what we want. We want this here. This is our compound here. So the desired compound was this guy here, and we made this compound, right? This is the enolate that we care about here. And obviously, because we decarboxylated this here, obviously I get CO2, right? So this here plus, whoops, still in box mode. This here is, I also have CO2 plus CO2. So that's kind of my the mechanism for this one here. So let me look at the answer here. Again, NaOH, that's good. It's attacking the acidic proton. You get a carbocation, that's good, which is exactly the same thing I did. Let me just zoom out for a sec and go back towards it. Again, I have a negative, negatively charged, the propyl group is going to come attached to here, to attach the carbocation. That's great. It creates this longer chain. That's good. It then undergoes a hydrolysis reaction, so it splits up into its carboxylic acid and then its alcohol. That's great. Acid workup makes it the alcohol, and then decarboxylation reaction. That's good. So CO2 gets removed. I'm left with this compound here. Again, this then this would make the double bond across here, right? Because it's going to then kick out this the extra bond here. It's going to become make it here. It's just like in a resonance structure. I get CO2 obviously, and then the ketoenol tautomerization gives me a ketone. So this solution here is correct. Great solution. Actually, a perfect solution here. Great solution and analysis. Love the use of mechanisms. Solution here is correct.